So I'm just going to dive straight into it. You've heard a lot about eutrophication over the last few days, but what are the actual implications for biological control? Well, we all know that nitrogen and phosphorus strongly influence the growth of freshwater macrophytes, and this in turn can have major effects on the success of biological control program. In three ways mainly. Firstly, the life cycle of the plant and the potential agent. Secondly, the damage that the agent can influence on the plants and the different nutrient levels. And thirdly, the actual competitive interactions of the invasive species and the indigenous species and the agent, and its also indigenous competitors. So how do scientists actually tease this apart? Well, manipulative experiments are undertaken to understand the capabilities and limitations of both the control agents and the weeds. And the general practice of doing this is to use controlled release fertilizers to create different levels of eutrophication. But very little is known about the actual release of these nutrients into their aquatic environments, and this could significantly or really confound our results. So the aim of this project was to investigate and quantify the dynamics of commercial control release fertilizers and fresh water under a variety of nutrient uptake conditions over a range of temperature and concentration parameters. So our weapon of choice was multi-coat by Hafer, and one very important thing going into this talk is that this is a soil product. Okay? It's used in agriculture, potted plants, it's meant for terrestrial use. So a couple of its principles, or a bit about it, it consists of polymer coating, and the thickness of this polymer coating actually determines the longevity of the product. The release of the nutrients into the environment is through diffusion, and it provides nutrients at measured proportions according to the environment's growth needs. And according to Hafer, the main release controlling factor is actually temperature. So here's a little graph from the Hafer website, and we can see on the y-axis we've got percentage release, on the x-axis over time, and we can see there's a very small lag phase followed by a linear release and a relatively long decay phase. So our methods, well, we decided on 3 different nutrient levels, and these nutrient levels can be traced back to past work and also can be directly related to levels of eutrophication in our environment. And we subjected them to 3 different treatments: a control, a plant only, and a plant and insect. Our plant of choice was Pistia stratiotes, water lettuce, and its very well known control agent, the Brazilian weevil, Neohydronomys affinis. Over and above actually looking at the fertilizer release rate, we incorporated the plant's response to feeding damage, different nutrient levels, evapotranspiration. Did PAR have an effect on the actual release of the nutrients into the system? And lastly, did different temperatures actually change the release rate? So diving into very simple results. So we can see from the graph here, on our y-axis we've got the total nitrogen in milligrams per litre, and on our x-axis number of days. And for all 3 treatments, well, this is the control, remember no plant and insect, the release of nutrients, the release of nitrogen into the system actually only happened on day 6. And we'll start down at the bottom in the low control, and these red lines indicate the total amount of nitrogen we added into the system. And we can see on day 6 there was actually a 100% release into the system, and for the next 10 days we were picking up more nitrogen in our tanks than what we actually expected that we put in. Moving on to the medium control, day 6 again, and there's a very, very slow release for the next 10 days, and on day 16, 17, 18 we can start to actually see a little bit of a linear release. What I found extremely interesting about the study, and could have massive implications on past studies and also our mass rearing programs, was our high control. So we can see here that we put in 50.5 milligrams of nitrogen per litre into the system, and after 18 days of running the experiment, we're still registering less than 10 milligrams of nitrogen per litre, which could have massive implications for confounding results. So just to summarise, this baseline study will be essential for improving current laboratory strategies for the prediction of plant invasion success driven by nutrient loading. I'd just like to say thank you very much for listening, and I look forward to answering any questions you have later.